Dry heat sterilisation. Now, dry heat sterilisation is the basis of depyrogenation tunnels. Now, the definition of depyrogenation by dry heat is well defined in the United States Pharmacopoeia, and this is designed to achieve a 3-log reduction at a particular temperature over a particular time. Now, commonly, most depyrogenation tunnels are designed to run at over 250 degrees Celsius, and theoretically, depyrogenation can be achieved in a time of less than 1 minute. Often, higher temperatures, slightly longer times, are built in to achieve overkill. Okay, I'm going to change topic. I'm going to move on to clean rooms. Now, clean rooms are covered to an extent within this module, particularly around aseptic filling. For those of you who have taken or are intending to take PMAT Module 3 on environmental monitoring, there's far greater detail about clean rooms in that particular text. So a clean room is a room that is especially designed to create a clean environment, and clean is defined purely by the concentration of particulates in a given volume of air. That given volume of air is 1 cubic metre, and that's laid out in an international standard on clean rooms called ISO 14644. Now that standard applies to the electronics industry as much as it applies to the pharmaceutical industry. Additionally, GMP also requires that there's certain limitations placed on the maximum number of viable microorganisms permitted. So it overlays the core clean room definition. Okay, so we're coming up to another exercise. I'd like to consider what's special about the air in clean rooms that helps to make a clean room clean. So again, if you could go into groups, if you can consider this question for 5 to 10 minutes, if you can then report back and share your answers with the other members of the class, and then I'll be back to give you my thoughts. So if the person in charge of the video can now pause it, and I'll see you in a few minutes. Welcome back. So that was your question. What's special about the air in clean rooms? Hope you had some reasonable answers. Here are a few of my thoughts. Okay, to me there are 4 principles which apply to the control of airborne microorganisms in clean rooms. Essentially, these are fundamental design concepts. And these concepts are filtration, dilution, air movement, and directional air flow. So, looking at the first of these, filtration. Okay? So, our clean rooms have HEPA filters. HEPA filter is an acronym for high efficiency particulate air. And these filter the air coming into the clean room. And these are designed if the standard one, it has an efficiency rating of 99.997%. And this is then designed to capture most of the particles in the air and stop them going into the clean room. Now, to make HEPA filters more efficient, they're actually protected from blockage by having pre-filters in place. And these actually help reduce 90% of the particles in the air. Now, HEPA filters work in different ways. Essentially, they strain and sieve out the particles between 2 filter fibres that are arranged in something like a concertina effect, a bit like an accordion. And the 3 methods that they capture particles are by inception, so where particles hit the fibres and adhere to them; impaction, where forces the particles to be lodged into the fibres; and diffusion, where as a result with the collision of gas molecules, the path of particles are impeded and delayed. In Grade A ISO Class 5 clean zones, HEPA filters also help to straighten the airflow, and that's one of the measures towards creating unidirectional airflow. One of the most important tests on a HEPA filter is to check it for leaks to ensure that it's not leaking and particles aren't getting through edges around the filter. Okay, our second key clean room concept is dilution. And this is a natural thing where if we have a room without very much ventilation in it, particles are going to build up. So we need to create lots of ventilation in the clean room to ensure that particles generated in the clean room are carried away with clean air, and clean air keeps coming in, refreshing the clean room and helps dilute the particles out. And this is achieved and measured by having a suitably high number of air changes per hour. A modern clean room would have at least 40 air changes per hour. Our next clean room concept, number 3, is air movement. So we want to avoid any particles in the air, be these microorganisms, from settling out. So we want to keep the air in the clean room moving constantly. Therefore, we want to have good turbulent airflow in most clean rooms and in clean zones. In unidirectional airflow cabinets, we want to have fast, rapid air going in one direction. Finally, we have directional airflow, and this is about pressure differentials. And this is to have air in a very clean area blowing outwards into a less clean area, and having it so that the air from the less clean area cannot blow into the clean area. And this is created by having a pressure differential, and we measure pressure with the current SI unit of pascals, and normally areas are at least 15, often 20 pascals higher for the cleaner area to the less clean area. So these concepts may be a little difficult to take in if you're not used to clean rooms, but they are explained at length in the module. There are other aspects of clean room that help reduce contamination. Temperature, because we don't want our operators to be perspiring too much. Appropriate gowning, we want our operators in clean rooms to wear the right type of clothing and to go through changing rooms. We want to have validated disinfection practices, and we want to be able to transfer materials and people in and out of clean rooms in the cleanest possible manner. So we have a picture on the screen here which is looking at clean rooms, and it's a simplified diagram of an aseptic filling area. So you'll see there that if you start off on the left hand side where it says materials entry, beneath that is personnel entry. So you have the people coming in one way, materials coming in the other way. They're then transported into the support area, and they will then enter into the green shaded area through either hatches for transferring in materials, directly by autoclaving or through hot air ovens. Then we have our cleanest area, which is the green area, which is the filling room, and then the hatched area is where the product's actually filled. And then importantly, onto the right hand side, where it says personnel access, it's a different way for people to get out of the clean room. This diagram is in your course notes, so you can study that in more detail, but it's just to give you a flavour of the clean room design concept. Although clean rooms are good, we get better assurance from the use of isolators and RABs. RAB stands for Restricted Access Barrier System. Both are containment environments, and they use barrier technology to create enclosed workspaces, which mean that people do not directly interact with those workspaces, thereby affording us greater control and less chance of contamination ingress. And as I said there, PMAT 3 is the core environmental clean room module, but there's interesting material in this PMAT 4 module. Okay, I'd like to now have a look at quality control and have a look at sterility testing, parametric release and biological indicators. So first of all, it's time for another exercise, and I'd like you to go into groups, and I'd like you to write down and debate. What is the sterility test? Here's the controversial question. Is the sterility test any good? Does it actually mean anything? And are there better ways to assess sterility assurance in pharmaceutical processing? So if you take about 10 minutes or so, have a group discussion, then come back, share your ideas, and then I'll be back with some of my thoughts. So if the person looking after the video can now pause it, I'll be back in a minute. Welcome back. So I hope you enjoyed that exercise. Maybe you come up with a couple of controversial points. I'll give you my thoughts now. Okay, so the sterility test is either the cultural-based method as described in the Pharmacopoeia, or it's a rapid or alternative method. Now, in 2012, the FDA permitted the use of rapid and alternative sterility test methods, which meant that people can move away from the Pharmacopoeia to either use methods that have more chance of picking up contamination, or to use methods that give a result far more quickly, in maybe 3 days, rather than the typical 14 days prescribed in the cultural-based methods. And in the module, you'll find some information about the cultural method and the rapid method. Okay, so the culture method is a confirmation of non-sterility. It's not a confirmation of sterility. Okay, so it will say whether you've got a non-sterile product, but it doesn't really give you many guarantees that you've got a sterile product. You can only really assume sterility from the absence of growth. It's a weak method, okay, because it only tests a very small sample size. So if you fill 10,000 vials, your chance of detecting contamination is very slim, because the Pharmacopoeia recommends that you only test 20 items. So for example, if 5% of your batch is contaminated and you only test 10 samples for sterility and you do 100 sterility tests, 84 of those sterility tests will pass. So it's a very, very poor method of detection. There's also limitations in terms of culture media, type of culture media, the time and the temperature. And it's also not very good at picking up what we call viable but non-culturable microorganisms. So it's been estimated that only about 10% of the microorganisms found in the environment can actually grow on culture media. So the sterility test is then, being a cultural-based method, poor at picking up that level of contamination. So arguably, we get a better assurance of sterility from environmental control, having good aseptic practices, from doing bioburden assessments throughout the manufacture of the batch, and from environmental monitoring. Now, with terminal sterilisation, cases can be made for parametric release. Parametric release is really basically a decision to release a product in lieu of an end product sterility test. So it means collecting lots of information about environmental controls, with things at the right temperature, with products mixed for the right length of time. It's also about collecting lots of environmental monitoring data. Importantly, it cannot be used for aseptically filled products, and to make the case for parametric release, the case has to be made to a regulatory authority. However, it is a bit of a buzz thing, and it fits in with the current ICH Q9 guidance on quality risk management. It fits in with quality by design concepts, which the FDA favour. Fits in with the FDA process analytical technology initiatives, which is about real-time measurement of processing. But for it to work, you've got to have properly validated sterilisation processes. You've really got to understand your product bioburden. How high is the bioburden on the product before you present it to the steriliser? Very important to know that. And you need to have good environmental control. Okay, so one way to assess terminal sterilisation is using biological indicators. So it's time for another group exercise. I'd like you to consider what are the key criteria for biological indicators, and what are the different types of biological indicators available, and what might they be used for. So again, please go into groups, spend 5 or 10 minutes discussing it, then feed back to the others, have a discussion, and I'll be back with my thoughts shortly. So please can the video be paused, and I'll be back in a minute. Welcome back. So that was an exercise on biological indicators. So a biological indicator must come with a certificate of conformity, and the key criteria are: it must have a defined population, the microorganism must have a defined resistance, which is called the D value, and it must be pure. The D value is a very important concept, which I'll explain in a moment. So purity, it's not impossible that biological indicators manufactured in the factory will contain other microorganisms, so you need to be sure that the biological indicator you're using only contains the microorganism you want it to contain. So for example, if you're using BIs for steam sterilisation, you only want them to contain Geobacillus sterothermophilus, and that's assessed through phenotypic identification. And there's an electron micrograph on the screen there, which is looking at bacterial spores put onto rubber, and this particular one, you won't be able to see in detail here, but that picture is reproduced in your course notes, wasn't pure. So it does show that sometimes not all biological indicators are pure. Population, you have to have a defined population. And the pharmacopoeias say that's a minimum of 5 times 10 to the power of 5. Often it's 1 million. And you need to verify the population. And the USP, Chapter 55, offers some guidance on how to do that. And there's acceptance criteria that you need to be within 50% and 300% of the certified population on the BI. D-value, as I said, is arguably the most important concept. And this is defined as the decimal reduction value. And the D-value is the time taken to reduce the population of a known microorganism by 1 log, which is equivalent to 90% of the original starting population. Therefore, if an organism is reduced by 1D, it means that only 10% of the original population remains. So if a BI comes labelled with a D-value of 121 degrees for 1.5 minutes, it means that if we put 1 million cells in and we put them into autoclave, and the autoclave went to 121 degrees, 1 minute later that 1 million population will reduce by 90%. And you can see that by running an autoclave cycle for 15 minutes, we're building in massive overkill, because each then subsequent minute reduces that surviving population again by another 90%, another 90%, another 90%, and so on. BIs need to be checked and verified, and that's done by a special device called a beer vessel. Unfortunately not the kind of beer that can be drunk, but the kind of beer that stands for biological indicator equipment resistometer, and they're highly specialised equipment, and there's more details about those in your course notes. Other factors need to be considered when using biological indicators include the shelf life, the strip size, the package size, whether a Z value is needed. Now the Z value is defined as the number of degrees Celsius required to change the D value by a factor of 10. And the Z value is discussed at length in the course as well. So don't worry about these concepts so much at this stage, but as you're reading through and preparing for the later part of the course, take into account D values, Z values, populations and purity. Right, now we've now reached the end of the presentation, so I'd like to run through a little bit about the exam, preparing for the exam, and on the communication front, ways you can contact me. So I'm just going to come back up to the front and just run through some of the things about the examination. so I hope the run through about the module was interesting. That was designed to pick up some of the key concepts of the module so that you can best understand some of the more difficult things, give you an overview and a flavour of what's like to come up. But anyway, moving on to the dreaded exam. The exam is 2 hours long and it's going to be divided into 2 parts. Part A is structured questions, okay? And there are 4 questions and you have to answer all 4 questions. And they represent 40% of the marks. And they're designed to really test your learning. So it's key concepts. So it might be, for instance, what is a unidirectional airflow device? And you may write down a short answer to that. Part B is essay questions. Now, what I'm doing in the exam, there are 3 essays, and you have to answer 1 of those. And you need to write your answer in an essay style. And these are really weighing up theoretical concepts you picked up on the course and tying those to a few practical examples. And the essay accounts for 60% of the marks. Okay, just a possible approach. If some of you haven't written an essay for a few years, then I suggest that you plan your answer for about 10 minutes. You can scribble on the exam paper for that, as long as you cross it through. Then you write your essay for about 25 minutes. And then it's always useful to spend about 5 minutes just checking your answer, making sure you've got all of the key concepts that you want to capture. But we discuss exam technique throughout the tutorials. Okay, so just to conclude, I've put on the screen here my contact details. So I have my work email address, my home email address, and there's just a reminder there about the Pharmaceutical Microbiology website. It has a whole range of interesting topics and discussions and is often updated on a daily basis. So I'll just let you have a look at those and write those down if you need to. Okay, so I hope you found this interesting. I would like to apologise again for not being able to be with you today, but I have a serious work incident has occurred. However, I'm intending to be at the summer school on Saturday, tomorrow, and there'll be an opportunity for tutorials, and these can be on a one-to-one basis, and you can ask me any questions about this module or any of the other modules that I tutor, and on the exam and so on. So I hope you found this session of interest, and I wish you the best of luck with your studies and enjoying this richly interesting sterilisation material. So thank you and goodbye.